Very good morning, my dear students. Today we shall discuss about the model number 5, design of a steel beam. In this, we will talk about short notes on lateral stability of a beam, as well as what are the factors affecting lateral stability, behavior of a beam in bending, and later we will be talking about two types of beam, basically lateral supported and lateral unsupported. Unfortunately, in syllabus we have only laterally supported beams, and later we'll be talking about the beam to beam connections, beam to column connections, and the column splices later in the syllabus. Hence, whenever we discuss about a beam, we analyze the beam for bending moment, we analyze for shear force, and we analyze for deflection. And after analyzing, the beam should not bend, beam should not have a shear force, not deflect. So hence we design for that. So we do check for bending strength, check for shear strength, as for check for deflection we do. Later we'll be talking about, as we're going to do an I section beam, we check for web buckling. That we'll be discussing later. What is web buckling as well as web crippling later. Now we shall try to understand what is meant by laterally supported beams here. What is a lateral supported beam means if the compression flange of an I section beam is embedded into the RCC slab, then you don't have any lateral deflection. Such kind of a beam is called as a laterally supported beam. Here you are seeing a pictorial representation of an I section with a compression flange embedded into the RCC slab. Such kind of a slab is called as a laterally supported beam. Like that, I have two secondary beams, 1 and 2, and in between that I have a main beam which is rigidly fixed. Such kind of beam is also called as laterally supported beam here. So hence, what is a laterally supported beam? As explained in the notes, that if I don't have a lateral deflection, hence such kind of beam is called as an laterally supported beam. As per the part of syllabus, we have only the design of laterally supported beam. So hence we will talk about step-by-step procedure of designing a laterally supported beam. Like we learned in the 5th semester of a design of a T-beam, the same kind of problem will be given here. Based on that, a classroom of dimensions 7 meters and 10 meters will be given. So hence intermediate beams are spaced at 3 meters. So hence you used to calculate the loads. So hence similar way, once you find out the loads, that is called as characteristic load or expected load. So hence we design as per the limit state design, that is the factor load is equal to the partial safety factor 1.5 into the working load. Then step number 2 is to find out the maximum bending moment and the maximum shear force. Apply the relevant formula. If it is a simply supported beam subjected to uniform distributed load, then the maximum bending moment will be m equal to w square by 8. If it is a point load, central point load, the maximum bending moment is m equal to wl by 4. And if the problem goes on changing with a different kind of loading, apply the basics of third semester strength of materials, find the maximum bending moment as well as find out the maximum shear force. Once you get a bending moment, this is a formula to find out the trial section here, where m is a bending moment, gamma m naught is 1.1 as per page number IS 800 2007, page number 30. F of 5 is not given a problem, always take as 250 Newton per mm square. Then we are going to refer page number 138 and 139 to find out the which section I have to provide. If by chance I select some ISMB 400 section, then you have to write down all the section properties referring the steel table or SP6. Later, once the section is identified, next to classify the section, whether it is a plastic, semi-compact, plastic or slender, I have to find out here. So this we are going to refer from page number 18 of IS 800 2007. Later, once we identify if it's a plastic or semi-plastic or compact or slender, Then we check for shear strength as per the page number 59 of IS 800 2007. VD is going to be F of 5 by root 3 comma m naught. H is the depth of the web. TW is the thickness of the web later, which we're going to refer from the steel cable. Then we check for it should be less than 0.6 times of VD or more than 0.6 VD for high shear case. The same way we check for bending strength here, and whatever the bending strength I get, that should be more than the actual bending, and then we tell the safer. So this we formulate the page number 53 of IS 802 and 2007. That I'll be showing it later. Once you check for shear strength and check for bending strength, then check for web buckling, web crippling, and deflection. So these are the three other checks we have to do. So what is meant by this formula is there, page number 67 of IS 800 2007, clause number 8.73.1 here. So hence, what do you mean by web buckling? Generally we provide an I section, and when the I section we provide, the web is of a longer length and it has an thinner at web part. So hence the web will try to buckle. So hence that should be safe against the web buckling. If by chance it fail, we are going to provide web stiffeners. So this is the web buckling procedure explained in the codebook procedure. So this is a pictorial representation where web is very thin member tries to buckle. Where the formula is given as B1. B1 is nothing but the width of the support provided at the supports. Detailed formulas are given in the codebook. Same we check for web crippling. Whenever the web is of a longer length at the supports or at the web portion, the web crippling may occur here. Again, the formula is given page number 67 of IS 800 2007 of 8.7.4. The problem. So this is what the checks we do for web buckling, web crippling. Only two different checks as new one what we learn here. Now the last one is called as check for deflection 5WL to the power of 4 by 3 to 4 by EI. It's wrongly written as WL square, WL to the power of 4. And later the permissive deflection is spanned by 300 as per page number 31 of IS 800 2007. So this is a step-by-step procedure of an numerical problem to be solved. So hence now we'll go into the numerical problem to understand the procedure of a problem. So here we'll be talking about a problem which we discussed in the 5th semester, design of a T-beam, where a classroom of dimension will be given of 7 meter into 15 meters, and the beams are spaced at 3 meters center to center will be given, and your job is to design the beam. So here this is the problem. Design a suitable beam for an classroom of dimension 7.5 meter to 12 meter. It consists of 100 mm thick RCC slab supported on steel beams spaced at 3 meters center to center. The finishing load, or it can be given as a floor load also, as 1 kilonewton per meter square, and the live load is given as 4 kilonewton. This can be given as an imposed load also. Self for the beam should be taken as 1 kilonewton per meter. The limiting deflection is spanned by 250, and the wall thickness is taken as 250 mm. So hence this is a small picture representation, 7.5 meter to 12 meters, and the beams are spaced at 3 meters center to center. So now the job is to design this intermediate beam. So in this intermediate beam, as this is 3 meter, this is 7.5, so this kind of slab is an one-way continuous slab. So hence the loads on this intermediate beam will be 50% of the WL by 2 comes on the beam, WL by 2 comes on this beam. The similar way, the imposed load here acting here also 50% comes on the beam, 50% comes on this beam. Later, you have something called as flow finished load that to be taken here 50%, 50%. Plus, you have the self weight of the beam to be taken as 1 kilonewton per meter. So this is the same as what we learned in the 5th semester design of an T-beam. So hence with that regard, the first one, the depth of the slab is given as D is equal to 100 mm in the problem, and the imposed load is given as 4 kN per meter square, as well as the flow finished load is 1 kN per meter square. So how do I calculate the load of the self weight of the slab? So thickness slab is 0.1 into half of this 1.5, 1.5, 1.5 plus 1.5 is 3 into the density of reinforced cement concrete is 25. Hence 0.1 into 3 into 25, you get 7.5 kilonewton per meter. Like that, you get the imposed load given in the problem, or live load is 4, and here also 50%, 50%, and 4 into 3, 12 kilonewton per meter. The same you have the flow finish, 1 kilonewton per meter, 1 into 3, 3 kilonewton per meter. Then self of the beam given in this problem is 1 kilonewton per meter, that you have taken here 1 kilonewton per meter. So hence, add up all that, I get the characteristic load as 23.5 kilonewton per meter. Now design load is equal to 23.5 into 1.5, I get 35.25 kilonewton per meter. As it is a simply supported beam, apply the formula bending moment is M is equal to WL square by 8. Apply here. Now how do I get 7.75? 7.75 is nothing but the effective span, that is center to center here. So here the span of the room is given as 7.5, and the wall thickness is given as 250 mm. So 7.5 plus 250 by 2 plus 250 by 2, I get 7.75 meter as effective span in the problem. So hence apply that effective span and calculate the bending moment here and the shear force. Once you have done that, the next step is to calculate a suitable section. I have told you the step-by-step procedure starting itself, but anyhow that formula how it has come. We know from the 3rd semester M by I by F by Y it need not be written in the examination. Straight away we can write down this formula. However, understanding written here I by Y F, and F to have a partial safety factor gamma M naught is used here. So hence ZP is equal to MD gamma M naught for F of phi for a transection. So substitute the bending moment value as 264 to 10 power 6. That is conversion into kilonewton meter into Newton mm, and gamma M naught as per page number 30 is 1.1 of IS 800-2007, and F of I is 250. Later we will be getting the ZP here. Now how do I take this ZP? So hence I told you you're going to refer page number 138 of IS 800-2007 there. So I got some 1,138 that you got in the terms of mm convert into centimeters. So this is the page what you're going to refer. So hence ZP is given here in centimeter cube. So as this is given centimeter cube, so whatever you calculate in mm cube, convert into centimeter cube and provide higher section. So usually we have various kinds of section. It's called ISWB, Indian Standard Wide Beam, ISLB, Indian Standard Light Beam, Indian Standard Medium Beam, Indian Standard Heavy Beam. So for practical application, always choose and preferably and ISMB section only in the problem. So hence, referring this page number 138 and 139 provide and suitable section. Once you have taken a suitable section, write down all the properties of the section, that is the depth of the web, breadth of the flange, thickness of the flange, as well as thickness of the web, all that. So all this information we are going to refer from the steel table, or there is SP6. So hence, so here referring the page 138, suitable section is taken ISMB 400, 61.5 kg per meter. So then we'll be calculating, write down the properties of that: ZP, ZE, H, breadth of the flange 140, thickness of flange, thickness of web DW, as well as radius of the fillet. Write down as R1, referring the steel table as 14 mm. Later, you have to classify this section B by TF. So hence, you have to refer page number 18 of IS 800 2007, where it gives how to classify a section. So this is the page to be referred. Hence, B by TF. B is called as the outstand of an I section. So I have taken ISMB 400. So for ISMB 400, the breadth of flange is 140, and this is a B. Hence 140 by 2 is 70 mm. 70 by TF. If it is less than 9.4, then it's called as plastic. And if it is more than 9.4, then it's called as compact. And if it is more than 10.5, it was semi-compact. If it is more than 15.7, it tells a slender. Like that, we have D by TW also. It is more than less than 84 epsilon, it's called as plastic. Like that, the classification given. What is epsilon? Epsilon is nothing but 250 by f of I. As f of I is 250, epsilon is always 1. So hence, with that regard, here as per the problem, B is equal to 70, that's 140 half by 16. So hence less than 9.4. Like that, D by TW. What is a D? How do I calculate? The overall depth is 400 minus 2 times of TF minus 2 times R1. So substitute the value of R1 here and you will be getting 340. So 340 by 8.4 lesser than 84. Hence it's both are plastic. If by chance one is plastic, one is slender, apply slender. So the critical one. So once it's the plastic, apply the relevant formula, find out how much bending strength it can take. And as in the simplest code being 278, 267, and the actual bending moment is lesser than that. So hence it is stronger, so it is safe against bending strength. Later check for the shear strength of the problem. So this is what I told you, step by step procedure. After finding out the bending strength, okay. So this is for check for shear strength. You do first page 59. The formula is given here neatly. Page 59, what I have discussed, and actual shear was 136, but this can take 0.6 times of VD 280, hence it is safe in a shear strength. Later you have to check for bending strength, page 53. If by chance if it is greater than 0.6 times VD, I have a different form to be used. So hence always check for shear strength and later check for bending strength. So here also the bending moment is lesser than the actual how much you can resist, hence it's safe against the bending strength. Later check for deflection. Span by 250 the permissive deflection as per IS 800 2007. So 7.75 the effective span, multiplying the 1000 to convert mm divided by 250, I get 31, and then the del permissible is 5 by 384 WL by EI. This is called del actual, hence I'll get 25.69. Hence based on that the three checks are over. And the two more checks to be checked for the web buckling and web crippling. As web crippling is a little easier one, we shall do that first. So hence referring page number 67, where B1 is called a stiff bearing length, always take the B1 is equal to 250 mm for a simply supported beam here, and N1 is the angle of dispersion to the flange of the web stiff, and the slope of 1 is 2.5. So hence here 2.5 means the cracks comes under this here, which I explained in the starting of the page. Hence R1 plus TF 14 plus 16, you get 30. Hence N2 is equal to 2.5 into 30 is 75. That you substitute as 75. This is the thickness of web, and this is the F of phi, and this is the gamma m naught. So 657, which is greater than the actual shear force, hence is safe against the web crippling. This is what the procedure is being adapted as per page number 67. The same way you have checked for web buckling. So what is the web buckling? Here we do again refer the page number 67 and do this problem. B1 is 250, N1 is called as the angle of dispersion at 45 degree, hence 400 by 12, 2, I get 200 mm. Then find out the area, that is 250 plus 200 into 8.9, I get 4000, substitute here, and then refer page 67 is a buckling class, C class, so hence refer page number 67 and get the buckling, and this formula you have to remember, 2.5 d times of tw. Find out the FCD, apply that, so you get the stress with 459 shear force, which is more than the actual shear force, hence it is safe. So this is regarding the design problem. The same way another problem was given in one of the examination, that is figure shows here. Here the second problem is given that ISMB section should be used, and the factor UDL is already given, there is no need to calculate, go with a similar procedure. Like that, in the third type of problem, figure shows a floor beam arrangement for a factory building. Framing consists of an RCC slab 120 mm thick of unfinished load, distributed load is given, and this the only concept is given as in the problem. The moving load is being given here, 40 kilonewton is given. It's only special in this problem. The problem is the same kind, except the 3 meters, it is 2 meters, but there's a moving load of 40 kilonewton. As when the fourth semester building structures or the structures we learned, maximum minimum occurs when the moving load is at the center, and the maximum shear force occurs when the support is at the one of the support. So hence calculate the loads as usual, what I explained earlier, but the moving load of 40 kilonewton, so this is the UDL, but the moving load is 60. So this is the formula for the moving load. Maximum minimum occurs when it is the center, so hence the WL by 4 is used. Like that, we have the maximum shear force occurs when the support is at the one of the support, so hence 60 is used here. So hence find out the maximum limit and maximum shear force. So later same procedure you adapt here in the problem. So this ends up the class for design of beams. In next class we'll talk about the analysis problem as well as some beam to beam connections, beam to column connections, as well as column splices. So if you have any doubts, you can call me on my mobile. So hence have a good day, stay safe, stay home. Thank you, thanks a lot.